morning, afternoon, good afternoon. As a reminder, the second week of Lab 3, which is next week, is also fall break, as you probably know. So first of all, lab will be open on the Tuesday of fall break from about 10 to 4. Second, the Tuesday night section will have a due date for their project demo of the Wednesday night section. But you can demo on Tuesday if you're ready, or Wednesday afternoon, or Wednesday morning. The lab is going to be open all the way from Wednesday 10 a.m. to 7:30, except for lecture. Although, maybe it'd be a good idea to just cancel lecture and have it in the lab on that Wednesday. Let me think about that. Does that sound like possibly a useful thing to do? I mean, we'll just go Wednesday 10 o'clock straight through. So the other thing about the second week of Lab 3 is that homework 5 is due in lab, out of order with homework 4. And that is your final project proposal. We need it due then so that week 1 you can get it back about week 1 of Lab 4 and start revising before the final project actually starts at the end of Lab 4. So next week, fall break, you're going to demo Lab 3 and hand in homework 5. Any questions on the logistics? But you have a clear idea what homework 5 is supposed to be. Final project proposal. I've been starting to hear some final project proposals. That's good. Any specific questions you have about them, feel free to ask during the lecture. That's fine. Otherwise, any questions on Lab 3? Let me remind you. Oh, yes.
Yeah, should we use PT Cornell 1.2 or 1.2.1?
Oh, so there is the main difference between 1.1 and 1.2 is in 1.1 there is no case statement support for threads. In 1.2, using a trick in GCC, there is support for case statements, and that's what you must use. However, 1.2.1 fixes a bug that was in 1.2 and in 1.1, which is related to the concurrency of the USART, Universal Asynchronous Receive Transmit. You're not going to be using the USART in Lab 3, but you will be using it in Lab 4, so you may as well start using 1.2.1 threads. The concurrency problem is that 1.2 does not wait for the last character to be transmitted before it starts the next transmission, therefore destroying a character at the UART, or USART. 1.2.1 interlocks so that it does not allow the spawn thread to exit until the last character is actually done transmitting. Thank you. Any other questions? So one of the questions that's come up in Lab 3 is student who, there we go, who was getting Vref going this morning as a DMA device and got no output, so I thought I would remind you that CVR, the voltage reference, is mostly meant to be an internal voltage reference. You can route it to an output pin, but you have to do a few bits of setup. And the setup is encapsulated in this variable CVRCon setup, which stores the config after you initialize it. So when you go down here and open CV reference open, we're going to, of course, enable it, because why would you not if you're going to use it? You're going to enable its output so that the output of the voltage reference is now connected to pin 25. And you're going to set the CREF range to low, and there's a technical thing that limits it to about 1.5 volts output, which is about right for the speakers. Then the register which actually that CVRef open actually modifies is called CVRCon. We're going to copy that back into CVRCon setup, because that is a bit pattern that's necessary to produce an output voltage, happens to have the value of hexadecimal 8060, and we can look up what that is, but you will notice that the low order 4 bits of that are 0, and that 4 bits is where you're going to insert the voltage value you want to output. So the voltage you output will always be hexadecimal 806 and then a digit between 0 and F, which will be the voltage itself. And so you have to send 2 bytes. It has to be a 16-bit transfer, DMA transfer, and the array that you build and send will have to be at least a 16-bit array, a short array. Could be an int, but could be a short. With the top 12 bits set to this pattern in the array. Because the DMA transfer can't do any arithmetic. It can't say OR together 2 values. So these values have to be ORed with your voltage in the array that you're going to send by DMA. And that's the only obscurity that I know of for setting up the DMA transfer. Any questions about the DMA transfer? You saw that there was a correction to Lab 3. I bounced that out as Piazza, and I think I also put it in Mail. There was a bad constant in the pseudo code. I hate that. But this value right here was originally a 2 and should have been a 4. The two balls can interact if they're more than 4 units apart, not 2 units apart. Any other questions about Lab 3? How many people have DMA running? 1, 2. Same group? Good. 2. 2 out of 35 groups. It's a start. How many people have balls flying around the screen? Good. 1 group. 2 group. Yes, I said rain. Yeah, okay. Oh, that's right. You guys are, yeah, right. That's the same group. And that's it? Okay, time's a-wasting, folks. So I can talk more about final projects if you have any specific questions. Otherwise, 1 week from tomorrow, 1 week from Wednesday, this is Monday, there's no lecture next Monday. 1 week from next Wednesday is the beginning of Lab 4. And so I need to start talking about Lab 4 so we can get through a bunch of material. We're going to be doing motor control in Lab 4. And so there's a bunch of peripherals we need to look at. We need to talk a little bit about motors, because I think that you probably haven't looked at DC motors very much in any classwork. And something about PID control, some sort of optimal controllers, and also about isolation to get rid of noise. We also need to talk about a new peripheral, which is pulse width modulator. This is a digital output whose average value, averaged over time, varies in an analog manner. So you can set a PWM from very low duty cycle to very high duty cycle. And if we were to average over 1 cycle length, this would have a low average, whereas averaging over 1 cycle length, this would have a high average. So we can change the effective average voltage when averaged over a long enough time. And in the case of Lab 4, the device which is doing the averaging will be the motor itself. The time constant of the motor itself will be slower by a couple of orders of magnitude than the PWM frequency that you're going to set, so that the motor will be the integrator that takes the average. And you're going to, and so the first question that will come out is, why not use a DAC? Well, in general, to drive a motor, you're going to need a fairly high current. And if you run a transistor in linear mode, you know that it dissipates unless it's fully on or fully off, right? If it's half on, if it's dissipating half the voltage, it's dissipating half the power. And for high power motors, you cannot afford to do that. Turns out for the motors we're using in Lab 4, you probably actually could do that. But for powering high power motors, you have to have a switch that's either on or off. And by using a PWM signal, the fast switch you're going to use, which is a FET, will be either on or off. We do need to talk some about the math of the PID stuff. And we need to talk a little bit about serial communication, which is an extraordinarily old method that uses ASCII encoding of characters, and for decades used what is called RS-232 voltage levels, but we're not going to use RS-232 voltage levels. This standard, serial communication standard, goes back to 1900. And originally was used to send data for telegraph or for teletype, in which the decoders were mechanical. So the scheme is extremely simple because it was originally designed to be decoded by a series of camshafts. And the reason it's still relevant at all is that almost every microcontroller made has at least one serial channel that allows you to cheaply and easily get information out of the CPU. So we need to talk a little bit about that. Most of the serial communication is hidden from you by the threads package, but you need to know a little bit about it so you know how to connect the serial to USB converter that will allow you to use this with your laptop, which probably does no longer have a RS-232 port. I'd be shocked if any. Does anybody have a laptop with an RS-232 port? Does anybody even know what it looks like? 9-pin D-sub. You got one? Yeah, all right, yeah. D-sub connector is a connector that looks like this. You probably recognize them as the connector that's used for VGA, but the D-sub size for serial is 9-pin, not 15. So we need to talk just a little bit about that. So what I'm going to have you build is a constant speed controller. Any questions on this? Just this outline. So it's going to be a constant speed controller. So what we're going to do is to have a fan, which I'm going to draw schematically as just 4 blades in the most pathetic fashion. But the fans you have will actually have 7 blades. 7? It's not a power of 2. Okay, so, and what we're going to do is we're going to set this up. Now I'm going to turn this sideways and draw it like this. And what we're going to do is we're going to set up an infrared emitter on one side of this and an infrared receiver on the other side, and they're going to point towards each other. Or you're going to set this up, or you're going to paint white dots on the fan blades and reflect the infrared off the fan blades, your choice. The advantage of this is that the emitter and the transmitter can be side by side, so it's a little easier to set up the circuit board. The advantage of this is that the signal to noise ratio is huge. That's good. So we're going to have a sensor that can tell when a fan blade comes through, and what we're going to ask you to do is hold a constant speed. We're going to ask you to regulate that speed with a control circuit. And we're going to ask you, as part of the lab evaluation, to step that speed from, say, 500 to 1000 RPM. And then we're going to ask your circuit to, as accurately as possible, settle on the new voltage, on the new speed. And that would not be a good response. What I'd like to see is a response that settles quickly and accurately at the new value. So the infrared sensor is going to go through some sort of amplifier to get the level up to logic levels. We're going to put this then into the input capture. Remember that? Input capture? The input capture input of the PIC32, but not the input comparator, just the input capture pin. PIC32 is then going to run a PID algorithm, output a PWM signal, which is going to go to a opto isolator. That's for noise isolation. We'll talk about that in some more depth. Then that is going to go to a motor driver. And then to the motor, which of course is sensed by the opto. So it closes the loop. Most of the complexity of this lab, unlike the last lab, is hardware. You're going to be debugging a ton of hardware. That means that you need to have a good strategy for debugging hardware. In particular, the signal side is completely separate from the motor driver side. That suggests that one person could work on one and the other person could work on another one. But you're going to have to make the errors observable. One of the things I'm going to ask you to do to make errors observable is that there's going to be a PWM that drives the motor, but I'm going to also ask you to use the input capture, which is going to, the input capture is going to give you the time between pulses, right? The time between crossings of blades. I'm going to ask you to convert this to another PWM channel and output this to the scope. There's going to have to be a low-pass filter here. The PWM here is going to need a low-pass filter and go to the scope. And so this is going to be RPM, and this is going to be the command to the motor. And to debug this thing, you're going to have to make both of those visible. And so the first thing you should do is get the two channels working, not the last thing. Oh, we need to read out the RPM also. It's extremely helpful for debugging if this is working from the beginning. So there's lots of hardware steps here. Any questions? We're going to talk about yet another connection scheme for the hardware. We're going to give you one of two different serial cables. They were bought at different times for different reasons. I'm sad I did that, but that's the way it is. There's two different serial configurations. You're going to have to connect them correctly. Both of these serial cables you're going to hook up with the PIC32 at the wire terminated end and the USB connection to your laptop. Both of these serial cables have a pin on them that gives you access to 5-volt USB power. If you connect that to anything, you're asking for trouble. You do not use any of the USB power for anything in this lab. Let's say you hook it to the VDD pin. The next step is you throw away the board. Then you get chewed out, and then you get another board. The next time you do it, you lose points. Don't hook up VDD. Hook up a transmit line, a receive line, and a ground. It says this in some detail. We'll talk more about that. Infrared sensor circuit is going to look something like this. You're going to have an infrared LED and a photo transistor, and for reasons that escape me, maybe somebody can come up with a justification for this. The long lead on the LED is the positive side, and on the long lead on the phototransistor is the negative side. So given the first thing you're going to do, of course, is make sure that you're emitting light and receiving light. So the first thing you're going to do is build this little circuit and then put your finger in between it and see if it changes. What are you going to do if it doesn't change? What's the first thing you're going to do? Change the polarity of the infrared emitter. Yeah, that's probably pop it out, turn it around. That's a good first step. Let's say that that doesn't work. Let's say, how can you tell if an infrared emitter is emitting? Probably most of you don't see infrared. Maybe one or two of you do. Your cell phone camera can see infrared often, not always, but most of them will. It comes across as kind of a weird purplish color. But there's even an easier way. Based on the voltage across the diode. What is the forward voltage drop of an infrared diode? What is the band gap of an infrared diode? Anybody know? You know what's the band gap of a silicon diode? 0.7. This is higher. It turns out that the band gap of a infrared diode is about 1.2 volts. So if this thing is conducting, there should be a 1 to 1.2 volt drop across the diode. If you see that, it's working. It's putting out something. It turns out that if you pump these babies up, if you replace this with this 300 ohm with a 100 ohm, don't do this necessarily. But you can actually feel the infrared on your lips, which are quite sensitive to heat. You can feel the infrared beam coming out of this thing. That's okay to do. Don't point it into your eye. But a much safer thing to do is to use the voltage across here. All right, once that's emitting, then you're going to want to see if the phototransistor is working. And of course, you're going to hook up a scope here. By the way, the LED that we have is a lens top LED. So if you look at this thing in cross section, it looks like this. There's a little flange and then two leads that come out. And all of the light comes out in a beam about 20 degrees across. All of it. That means if you point the receiver at the side of this, you see nothing. So these have to be pointing at each other. Now, that's not exactly true. 99% of the light comes out the front. If you put them exactly side by side, just right up against each other like this, and the LED is just slightly behind the phototransistor, you'll get a little scatter into the phototransistor, and the transistor will always be on. And the symptom will be, that's funny, the voltage here is always less than VDD. If the transistor is on, it pulls that voltage down. That's funny, it's always at ground. And so if you're doing a reflection mode where you're asking the light to come out of the LED, bounce off something, and come back to the detector, what you better do is to put something opaque between the two, like a piece of electrical tape. Paper's not good enough. Even black paper is not good enough. Electrical tape is just about good enough. Or ESD foam is even better. But basically, these things have to be able to see each other. They have to look right at each other. Coming off of there, we're going to feed the signal through a comparator to bring the voltage change up to logic levels. We're going to use a rail-to-rail op-amp. These are fairly slow op-amps, but that's okay because it's a fairly slow signal that we're getting through this system. If you figure these, the maximum speed of these fans is about 3,000 RPM. That sounds like 50 revolutions per second. There's 7 blades, that's 350 pulses per second. That's really slow. So the bandwidth is low. And you're going to ask, why don't we use the internal comparator? Why not? This is a really crummy signal coming out of here because there's serrations in the edge of the blades. The blades there's some shaking in the fan. It's a noisy signal. And so if you have a noisy signal that's coming up through some comparator threshold, you can get one or two transitions on the noise. So we have to add some hysteresis to the system, and you can't do that on the internal comparator because you don't have access to all of the leads. So what we're going to do is use an external comparator with a variable threshold. You're going to set the threshold here for the voltage that you're going to detect, and the ratio of these two resistances sets the dead zone hysteresis. Once you go above this by a certain amount, you have to go below the threshold by a certain amount to snap the system back to the other state. So the feedback resistor, and I think 1 meg is about right, the 1 meg feedback resistor gives you some hysteresis to make a cleaner, faster transitioning signal between on a noisy input waveform. And again, we have to use the external comparator because you can't get to the negative input of the comparator, internal comparator. So one person could debug that piece of circuitry. And this was an early attempt where I just put one dot on the hub and then put the LEDs side by side. Notice that the infrared LED is in front of the sensor because almost no light comes out the back of the LED. But it turns out that was a bad idea for at least two reasons. Number one, the voltage changes are small, on the order of a half a volt or so. Number two, with one dot on the hub, you get 1 pulse per revolution. Oh, well, that sounds good. I get 1 pulse per revolution. That's easy to calculate. I can divide by 1 in my head. But the fact is that the system has to go 1 whole revolution before you get any more data out. So your PID controller is waiting a 50th of a second or longer before it can do anything because there's no new data. If you put dots on the blades instead, you can just barely see the blades up here. If you get dots on the blades, you get data at 7 times the rate, and that cuts down the control delay by a factor of 7. Any of you taken control theory? So you know that a delay is equivalent to a phase shift, and negative phase shifts are bad for stability. So anytime you can drop a phase shift by, say, getting rid of a delay in the system, you make the system more stable. So again, either put a dot on each fan blade or use transmission across the fan blades, which is what I recommend. Let's talk a little bit about motors before we talk about this. Just a little bit about motors. Then we'll do the full hideous Kirchhoff's law motor equations next time. But for now, we're just going to model a motor as something that looks like we have some V across the motor, and this is some speed that comes out, and we get a more or less linear line. And we can model this as, for purposes today, of a PWM switch that we're going to turn on and off, and an inductor to ground, and we're going to call this the motor. And you'll remember that for this motor that V is equal to L di dt. So we turn on the motor. So let's turn on the motor and plot time this way and Vm this way. We turn on the motor here, motor on. Voltage hops up. It's kind of noisy perhaps because of motor generated EMFs we're going to talk about next time in some detail. Every motor is also a generator, right? So there's some noise on it, and we plot the current on the same time scale, and we find that the current is high and then drops back. This is I versus T, because as the speed goes up, the current goes down in a motor. And then we ask, what happens when we turn off the switch? What happens to the voltage? Inductor. Inductors, you remember from someplace way back in the dim memories of 2100, are like to keep the current constant through themselves, right? They want to maintain a constant current. So you open this switch, the inductor wants to keep the current flowing this way through an infinite resistance. And what happens to the voltage? It goes to infinity. Well, nothing ever goes to infinity, but in fact it becomes pretty big, negative, and can reach, say, minus 1,000 volts or so easily, even with a mechanical switch. Now, so why doesn't it go to infinity? What happens to limit it? The air breaks down. It sparks. It makes an arc. You get enough voltage generated to dissipate the energy through an arc. So now let's say that this switch happens to be a field effect transistor rather than a mechanical switch. You pop it open in a nanosecond, and what happens? The magic smoke comes out, and it's no longer a FET. It's an open circuit. So you got to do something to protect the switch against the high di dt. You must do that on every switched motor connection. Furthermore, some of the noise that's coming out of the motor, depending on the make of the motor and what kind of motor it is, some of the noise can be up into the RF region and can start interfering with your measurement, with your RPM measurement. So it's a really good idea to do a minimum of two things, no matter what the motor controller is. The first is to put a diode across the motor, reverse bias diode, which will turn on as soon as di/dt gets big enough and short out the high voltage. It'll keep the voltage down at 0.7 volts or 1 volt or so, unless you exceed the energy rating of the diode. So you absolutely must, on any DC motor, put a shunt diode, or it's called a snubber diode or a shunt diode or various other things, but put a back reverse diode on the motor. And note that if you put this on in the wrong direction, then whenever you turn on the motor, it shorts out the power supply. And so the symptom will be, that's funny, the voltage dropped. Right, so you want to make sure you get the polarity right. And to cut off the RF at the source, you want to short out the RF with a small, say a 0.1 microfarad disc-ceramic capacitor. So that'll get rid of this gigantic negative spike and also any noise that might be generated by the motor. Brushed motors make more noise than brushless motors. The motors we have are brushless. I don't think this is a big problem in our case, but DIDT is clearly a problem. We're going to be turning these motors on and off very quickly. Now, we're going to opto-isolate these two, not because it's so necessary for this lab, but because it is obsessively good practice when you're dealing with motors. For instance, I saw a final project maybe 10 years ago before I knew anything about opto-isolation of motors, maybe 20 years ago. And what they had done was to connect the output pin of a microcontroller directly to the gate of a field effect transistor which ran the motor. What they had was 3 motors on a ground effect car. So when all motors were running, this thing would hover above the ground. And you steered it by differential control of the 3 motors. So they'd turn on the first motor, it worked perfectly, they could control it. They'd turn on the second motor, and the system would start resetting about once every 5 seconds. You turn on the third motor, and it started resetting 10 times a second. You turn off the first 2 motors, leave the third motor on, must be bad third motor. Leave the third motor on, ran fine. Turn on the second motor, started resetting it about 1 every 10 seconds or so. So it was the sum of noise from the 3 motors that was being fed back into the ground line of the microcontroller and forcing the system to brown out reset, a power down reset. The way around that, which I started researching during that particular cycle, is to completely isolate the power supply for the motor from the power supply for the microcontroller. And this means no shared grounds, no shared nothing, no oscilloscope probes connected to both sides of the control circuit. There is no electrical connection between the motor driver and the microcontroller. So how does the signal get across? Optical. So inside the opto, this is a 6-pin P-dip. Inside the opto is going to be a infrared LED and another photo transistor, all in one package, and with no connection between the input and the output, and a voltage isolation of around 5,000 volts or so. So you can safely connect the LED to the port pin and connect the motor to a 12-volt source. In this case, you use the bench power supply for this side. The Agilent bench power supply, you'll set to 12 volts, run the motor off of that. And this side of the circuit can be completely tested and set up independently of even the software. You don't need any software to test this. All you need to do is be able to set this pin to 3 volts and ground. And you can test to make sure this whole circuit is correct and working. So even during lab 3, if you had somebody sitting around twiddling their thumbs, they could be starting on lab 4 by building this circuit.
Is this what's done in practice?
This is a fairly commonly used circuit, yes. It's a little dressed up. Typically, there wouldn't be quite so many resistors here, but basically there's some sort of opto switch connected to a big power transistor, yes. You will notice there is no value on that resistor because you have to choose it. We'll talk about that later. So the whole thing is going to be a closed circuit, a closed loop control system where the speed is, you're going to want to hold the speed constant, where you have to be able to step the speed. So you're going to want to be able to step the speed. In fact, the test situation that will be used will be 500 RPM to 1000 RPM, back down to 500 RPM. And what we would expect to see optimally is a slight overshoot with a settling and then an exponential decay back to 500. Why exponential decay? Because we're actually going to be building a nonlinear control system, because you can't slow the motor actively down. If the motor is going too fast, all you can do is turn off the control system and let the speed decay exponentially, as if it's a first order system. And that's, by the way, how you measure the time constant of the motor. You spin it passively with flicking a finger and watch the speed decay, and that gives you the decay time constant of the motor, which gives you something like the low pass characteristic of the motor itself. So again, this is primarily hardware. There's going to be a command interpreter which allows you to set speed. Come on. Which allows you to set speed, proportional, integral, and differential control parameters. But I'm going to give you an example of that, so I don't think that's going to be that hard to do. You have to worry a little about coherency and concurrency between the two threads. And the main thing is that there's going to be a compute thread which has to run as fast as possible to update the PID controller. Now, fast as possible, that's not quite right, because it doesn't make any sense to run it more than 350 times a second, because that's as often as you get new data from the sensor. But something around 100 a second or so. So we'll talk more about it next time. Lab will be open tomorrow morning at 9. Should anybody want to come in. Be open till 1 tomorrow. See you in lab.